Okay, welcome to the lecture, replacing the snow day lecture for Friday, February 14th. Happy Valentine's Day. So today we'll be talking about elastic and inelastic collisions. But let's start off with some review problems from the material from last time. So remember last time we did things like conservation of linear momentum, and also we talked about impulse for a collision. And so let's do a problem with linear momentum conservation. So here's the example. We have a 9,700 kilogram car is moving at 18 meters per second. I skipped the word moving. It's moving at 18 meters per second and hits a stationary vehicle. I call it a car, but it's probably more, it's going to end up being a lot bigger than a car. So let's say it's a truck or something. Stationary vehicle, the two stick together. And travel at 4 meters per second. And the question is, what is the mass of the originally stationary vehicle? Okay, so let's draw a little diagram of what we have initially. We have our 9,700 kilogram car going this way at 18 meters per second, and we have some big stationary object here with a mass m that we're trying to solve for, and it's not moving. And in the final picture, okay, we have the things stuck together. Maybe the fenders are attached. Mass m here, 9,700 kilograms, and this whole unit is moving at 4 meters per second. Okay, so we know that the total initial momentum must equal the total final momentum. So on the initial side, we will have the mass, 9,700 kilograms, times its velocity, 18 meters per second. By the way, I'm taking all this to be positive x-axis, so I'm getting the x components, plus the momentum for the stationary vehicle. It's not moving. That's not an arrow for its velocity. That's just the x-axis arrow. So no initial momentum for it. And now we have the final information. We have that an object that's the two masses stuck together, that's the mass, times its velocity, 4 meters per second in the positive x direction. And now we just need to solve for m. So that's pretty straightforward. We have, so we can divide, okay, so let's see, so we're going to multiply these through. That will give us, well, okay, so I'm going to multiply these through and then divide by 4, and that will give us 9,700 kilograms plus m. Okay, this guy divided by 4 gets rid of that, and then I'll take 9,700 kilograms, 18 meters per second divided by 4, and that comes out to 43,650 kilograms. And so now we can solve for m equals to that. M is equal to 33,950 kilograms, so a big truck. Right. Okay, so if you have questions about that, send me an email. We'll go on now. Another review problem. So the example is a 0.2 kilogram ball is dropped from rest. From a height of 2 meters. Okay, when it strikes the floor, the velocity reverses its direction. Its direction without decreasing in magnitude. And today we'll actually give a name for that type of a collision, so that will be associated with what we call elastic collision. So an object is dropped and it bounces, and just before it hits the floor, it's going down. Okay, but then right after it bounces, it's going up. So that's a collision where the velocity keeps its magnitude, but it reverses its direction. And we'll be talking about that today. That's what's called an elastic collision. What we did previously was what's actually called an inelastic collision. I'll define all of this in today's lecture. It's inelastic because they don't bounce off, they stick together. In fact, this is what's called a perfectly inelastic, where the things really actually physically stick together. Okay, so this is what we'll be calling today an elastic collision. The velocity reverses its direction without decreasing its magnitude when it bounces. Okay, and the question is, if the ball is in contact for 40 milliseconds, that seems somewhat realistic. The question is, what is the average force exerted by the floor during that time? Okay, so this is kind of a multi-step problem, a little bit challenging. So we have a ball and it's being dropped a distance of 2 meters. Okay, so what do we know about this just before? First of all, we need to know what it's going to do just before it bounces. So during the fall, it's just falling. We've done those types of problems. So we know that, alright, so this is the positive y direction we're taking as positive. So AY is negative 9.8 meters per second squared. It's dropped from rest, so it will have a v0y equals to 0. That's initial velocity. And y minus y0, that it starts here, it ends up there. So that will be negative 2.0 meters because it falls. Okay, so we want to figure out the final velocity. So the final velocity, by final I mean just before it hits the ground. Alright? Because when we do these uniform acceleration problems, we never had a bounce before. So we're going to stop the clock right just before it bounces. Alright, so we don't have time here. And the formula we can use to get the final velocity is the v squared formula. The vy squared minus the v0y squared is equal to 2ay y minus y0. Okay, so then we have v0y squared. We have all these numbers, everything else we know. We know v0y, we know ay, and we know y minus y0. Okay, so this is actually 0, so that's easy. 2 times negative 9.8 is ay. Y minus y0 is negative 2. And so we get Vy is equal to plus or minus 6.26 meters per second. Okay? Now, just before it bounces, it's going downwards, so you can figure out that the sign should be Vy is equal to negative 6.2 meters per second. Okay. Now, we have to figure out next what happens during the bounce. Okay, so during the bounce, there's a change in the momentum. So that's the Vy right before the bounce. So during the bounce, we have a change in momentum. Okay, so delta Py, that's, remember, P, small p is the symbol for momentum, so delta is a change, and I make it y for the y component. So that will be m times Vy final, or actually, just to be clear, because we already used the words initial and final here, let's just say after bounce minus mvy before the bounce. Okay? So remember, P is equal to m times v, so I'm using the y component. So Py is equal to my, and delta is always the final minus the initial. I'm calling it after minus before the bounce. Okay, so this is what happens before, so that's Vy before. And then Vy after is just going to be positive, this number, positive 6.26 meters per second. Okay, because as I said, it's reversing its direction. It goes down and then it comes up with the same speed. Alright, but the mass we're told is 0.2. The final, after the bounce, the velocity is positive 6.26 meters per second. Before the bounce, we have, okay, the mass is 0.2. And before the bounce we have negative 6.26 meters per second. Okay, so that gives us about 2.5 kilograms meters per second. And now, that's also, by the way, that's what's also called the impulse in the y direction, impulse. If you want the fancy word for that, it's the impulse in the y direction. Okay, and now we can see what is the average force exerted by floor. Okay, so let's just think about the direction of the force exerted by the floor. The ball was going down. After the bounce, it's going up. So it's clear that the floor is pushing up on the ball, and so the force should actually be upwards. Okay, so Vy average will be delta Py divided by delta t. So that's the formula that we had last time. Okay, changed in the momentum divided by delta t. And so that will be equal to 2.50 kilogram meters per second divided by 0.040, or 40 milliseconds. So that's 62.6 newtons in the upward direction, pushing the ball up. You might, in the homework at some point, or some other problem, you might be asked, how about the average force of the ball exerted on the table? Well, the ball is actually going to push the table in the opposite direction. This is just Newton's second law. So the floor is pushing up with 62.6 newtons, but the ball is going to push the table down with 62.6 newtons. Okay? Alright, so if you have questions on that, send me an email. For now, we're going to go on to the new material for today, and that's talking about elastic and inelastic collisions. Alright, so elastic, you just saw, think of a hard rubber ball. Okay, you don't need to think of it, you can just see it here, something like that. An elastic collision, think of a hard rubber ball bouncing off a hard surface. Okay, like this. Alright, so if it was perfectly elastic, the ball would not lose any energy. It would actually bounce like this. Okay, that's sort of the ideal elastic collision. Alright. Now, inelastic, think of two cars smashing into each other, like the example we just did. Actually, it was a car and a stationary vehicle that ended up being more like a truck. Okay, so the reason that it's inelastic is because there is some loss of mechanical energy. What happens is that you have the two cars coming in, they have some shape, and when they collide, some of that energy goes into crumpling the car, and so they might even stick together, but it's not necessary. They might bounce off, but you lose some of the kinetic energy of that collision because it's deforming the shape of the car. So a nice example of that is this object here, which is just a bunch of magnetic spheres. This is like a little scientific toy that's fun to play with. You can do all kinds of weird things with it. But one of the things you can do is you can show an inelastic collision. So for example, compare this bouncing ball with this guy. Alright, notice this doesn't really bounce at all. The reason it doesn't bounce is because as it collides, it deforms, and a lot of its energy goes into deforming its shape, and so you essentially lose all of its kinetic energy into deforming this object. Okay. Now, so that's inelastic. The key thing to remember, though, in any collision, for any collision which is isolated. The word by isolated, I mean you have two things that are colliding, and those are the only things involved in the game. They collide and they bounce off, or they stick together, or whatever. But there's nothing else that's affecting the physics of these two balls, okay? So that's what I mean by isolated. The two objects that are colliding are isolated from everything else. For any collision which is isolated, the total momentum is conserved. Okay? So if I were to write this out the way we did last time with the fancy vector notation, you say that the total initial momentum is m1v1I. So remember, we'll have two objects, and then there's initial and final for each one. So I have the subscript 1 for object 1, subscript 2 for object 2, and I for initial, and F for final. Okay, so we have m1v1I plus m2v2I, that's the total initial momentum. Okay, and that must be equal to the total final momentum. That's m1v1F plus m2v2F. Alright, so that's true for any collision. Now, you might be a little bit confused, though, because we were talking about, in the beginning of the lecture, about something bouncing, our example. It seems like the momentum of the ball is being reversed by hitting the floor. So you might be confused as to what's going on. So let me give you an example of what's going on with a collision of an object against the big floor or some essentially stationary, seemingly stationary object. So the momentum of the ball is being reversed, but the total momentum is actually would be conserved if there wasn't a whole bunch of friction here. What's going on, if this was floating in space, is I have this big gold book which is much heavier, much more massive than this ball. In a collision, the ball comes in, it hits the book, and it bounces off with almost the same speed it came in with, but it's actually slightly less, and the ball is going to recoil, and the book is just going to recoil very, very slowly. But since the book is so much more massive than the ball, what will happen is it kind of looks like the book doesn't do anything and the ball just reverses its direction. But in reality what goes on is there is a conservation of momentum. Okay, the total momentum going in is the total momentum, initial is the total momentum out. So there is a conservation of momentum going on there. It's just the problem is that the velocity of the floor when something hits it is so small that sometimes you just throw it away. But this is actually still being this is still true. Okay. In other words, there's a very small velocity associated with the floor moving that balances out this equation here. All right. Now, the important thing to say for collision, so when you get a test problem and you have some collision, this is always true. No matter what kind of collision, either elastic or inelastic, this is true. Your total momentum is conserved if it's isolated. So if I'm talking about strategies on a test problem, you start with this, momentum conservation. Okay? Now what I'll talk about is what additional equation you can use. And for the additional equation, then you have to know what kind of equation do I have? Is it elastic or inelastic? Okay, so you start with momentum conservation, and what else can you do? So for an elastic collision, the kinetic energy remains the same. Kinetic energy is conserved. Okay, so this is only for an elastic collision. It's very special, and what it means is that the energy of motion, the kinetic energy, is not being absorbed into, for example, permanently deforming something. In elastic collision, things can, deform from the collision, but they actually bounce back. They get their original shape back, and that energy is then transferred back into the kinetic energy. Okay, so the kinetic energy of the system, the initial, is equal to the final. There is a brief moment where some of the kinetic energy is changed into potential energy. For example, when these balls are just briefly touching and nothing's moving. Okay, but then just a split second later, you have your kinetic energy back. Once the balls are not in contact, you'll find that the kinetic energy is conserved. Okay, so that's the sense in which the kinetic energy is remaining the same, except for that brief moment in time where things are maybe being deformed slightly because of the collision. After that point, the kinetic energy is the same as what came in. Okay, so kinetic energy is conserved, so now we need an object, we need an expression for the initial kinetic energy is equal to the final kinetic energy. Okay, so we can write that down. Kinetic energy is 1/2 mv squared, right? K is equal to 1/2 mv squared. So we do that for each object, 1/2 m1v1 initial squared. Sorry about this notation. There's a lot of things going on. I have particle 1, particle 2, initial and final. Okay, m1, 1/2 m1v1i squared. And then the initial kinetic energy for particle 2, m2v2i squared. And this is equal to 1/2 m1v1 final squared plus 1/2 m2v2 final squared. Okay? Alright, now let us simplify things. In the case where the collision is all along the x-axis. So right now we're talking about elastic collisions only. Okay, so when we have motion along the motion along the x-axis, so let me actually start a new page here. So for motion along x-axis, so we're doing the elastic collision. I can write it And now my notation gets a little uglier because I need, in addition to having 1 or 2 and I or F, I'm going to put a little X to remind me that these are X components and not magnitudes of velocities, okay? So if I'm going to have momentum conservation, that's the first thing. I have M1, V1, I, X direction. Okay, M2, V2, I, X direction. M1, V1, final, X direction. M2, V2, final, X direction. Okay, there's a lot of subscripts and superscripts going on here, but I think it's pretty straightforward. This is the initial X component of momentum for 1, initial X component of momentum for 2, final X component of momentum for 1, final X component of momentum for 2. Now we then have the kinetic energy conservation for the elastic collision. So then we have 1/2 m1 v1 I x squared, okay, and then we have 1/2 m2 v2 I x squared is equal to 1/2 m1 v1 final x squared plus 1/2 m2 v2 final x squared. Okay, these are formulas that you can use to solve for the unknowns. For example, you might be given the initial velocities of the balls, the masses, and you want to then solve for the two velocities, final velocities of the balls. You have two unknowns, you have two equations, so you can solve for them. All right, but these are somewhat inconvenient because they're quadratic equations, and in fact you have quadratic equations perhaps with two unknowns, and that is not maybe something you enjoy doing. So what we'll do is we will actually do a little bit of algebra here and simplify it so that we can replace this kind of complicated equation. Let's make this simpler. We're going to simplify this guy to write down an equivalent equation that doesn't involve squares of things. And the simplification that we can get is we can actually write down an equivalent equation like this. All right, and I'll write it down and I'll tell you what's going on. And so what I'm saying is you use this equation, but then you can replace this complicated equation for the kinetic energy conservation as the following. Minus V1 final x minus V2 final x. Okay. This V1 minus V2 initial is what I'll call the initial relative velocity. Remember doing relative velocity way back in the beginning of the course. When object 2 looks at object 1, it sees object 1 moving with V1 minus V2. You have to subtract your own velocity to see the relative velocity of somebody else compared to you. Whereas V1 final minus V2 final over here, that's just the final relative velocity. Alright, so what this is saying is that the relative velocity in the initial must be negative the relative velocity for the final. Let me try to convince you that this makes some sense. So let's go back to the ball hitting the wall. So when it comes in, all right. So let's think about you. This is object 2, and think about this guy as object 1. Okay, so the relative velocity of 1 relative to 2, so think of yourself, you're sitting right here, you're observing this ball, it's coming in towards you, okay? So before the collision, it's going to the left, after the collision, it's going to the right, and with this wall not moving very much at all, the ball will actually just reverse its direction while maintaining its magnitude. So essentially, the relative velocity just flips its sign from going this way, and then after the collision, it goes that way. So that's what this equation is actually saying for the general case, not just the case for a ball hitting a wall. It's saying that the relative velocity is going to flip its sign. So I'll try to give you another example of this. So let's say 1 is the green and 2 is the red. Okay, so then 1 relative to the green relative to red, right, is moving in that direction. The green is getting closer to the red. Okay, but then after the collision, the green relative to red is going away. They're getting further apart. So what has happened is the relative velocity just flips its sign without changing its magnitude. Right. That's what you can do for a purely one-dimensional collision, something along the x-axis. And that's actually a useful shortcut for solving these equations instead of using this guy. So you use this momentum conservation, this guy here, and you use this flipping of the initial of the relative velocity to solve for the elastic collision. Now, I have a derivation of this in my notes. Since I'm videotaping it, videotaping this lecture, I will give you the derivation. If you don't like derivations, you can just fast forward. It'll probably be about just 5 minutes of derivation that you can fast forward through. But if you want to see this, here's how I got this formula here. Okay, I'm going to take these two equations and I'm going to drive this guy here. So let me just rewrite things in a slightly different way. Here's the derivation. Okay, what I'll do, let's see, how can I do this? I can actually fold this so that you can see this sheet. Alright, what I'll do now is I will write the kinetic energy equation where I have all the m1s on one side. So I'm going to bring this guy over here. So I'll have 1/2 m1, and then I'll have the v1 ix squared minus the v1 fx squared. Okay, and then I'll have the m2s on this side. So I'll have 1/2 m2, and then I'll have v2 final x squared minus this guy that came over. Okay, v2 ix squared. Alright, and I'll do the same thing with the momentum conservation equation. I'll put the m1s on one side. v1 here, x. This guy comes over, so it would be minus v1 fx, like that. And then I'll put the m2s over here, so I'll have m2 v2 fx minus the guy coming over here has v2 ix. Okay. Now we're going to do something kind of crazy. We're going to divide one equation by the other, where we divide this guy by this, and we'll divide this guy by that. That's a kosher operation because they're equal. Okay, you're dividing by the same thing on both sides. And then I'm going to use the fact that a squared minus b squared, you probably have seen this, is equal to a minus b times a plus b. Okay, so notice that is the structure of this term here. Something squared minus something else squared, and then I'm going to divide it by that something minus something, that other something. Okay, so now there's a squared minus b squared. I'm going to divide by a minus b, and what will be left over is a plus b. Okay, so when I divide this side by this guy, the m1s will cancel. I'll get a 1/2, and then I'll have this guy plus this thing left over. So I'll have 1/2 v1 ix plus v1 final x is equal to 1/2. And I'll do the same thing over here. A squared minus b squared divided by a minus b will give me a plus b. So I'll end up with a factor of 1/2. The m2s go away. And then I'll have v2f plus v2 ix. Okay. Alright, then I can get rid of the 1/2s. And now what I can do is I can pull it back so that the initials are, rearrange things so that the initials are on one side, v1 ix minus v2 ix, and then the finals are on the other side. And let me actually write it, okay, so let's do it in two steps. v2 fx minus v1 fx, And then I'm going to write it the way I had it on before. I'll put a minus sign here and write this as v1fx minus v2fx. So that's the equation we had before that we wanted to derive, that the relative velocity is just flipping its sign. Okay? All right. So this is the end of the derivation. I'm going to just pause for a moment. So this is end of derivation, so that people who wanted to skip this can come back. They can see this right here. All right. And now we'll return back to the lecture. Now we'll talk about inelastic collisions. For inelastic collisions, we only use, this is important, just a moment. Yeah.
Sorry, Dean, you know there's a faculty meeting?
Oh.
Yeah, the discussion of the nuclear experiment position is on.
Oh, okay. I'm recording something right now. I'll be over there. Okay, so for inelastic collisions, sorry about that. Apparently there's a faculty meeting going on right now. I'll finish the lecture though. For inelastic collisions, we only use conservation of momentum. Okay? Nothing with kinetic energy. Kinetic energy is not conserved. What happens is there's, some of its energy is converted to other forms of energy, just like this thing we did before. Okay? It's being converted into deformation, energy needed to deform the object. Okay? So, so an example is what I'll call perfect, or actually the better term is completely inelastic collision is when two objects stick together. Okay, so we have initial, we have some object M1, V1I, and then we have M2, V2I, and then if this looks familiar, this was the problem we started off with today. Okay, then we have two things stuck together. I should draw them as though they're actually stuck together, and so this object is as a unit is moving with some V final. Okay, so there's only one equation. We only use momentum conservation, but you can solve the problem for, let's say, the final velocity, because there's only one unknown. They're not moving independently, so you only need one equation. So that's an easier problem, like you saw. The problem we just did with the car hitting the stationary vehicle was not so hard. So if the collision is along the x-axis, then we can write it as M1 V1IX plus M2 V2IX is equal to M1 plus M2 VFX. Okay. Very good. So I think we'll stop there. I have to go to a faculty meeting. But next time we'll do some examples with elastic collisions. And I'll ask if you have any questions on Monday. So I'll see you then. Bye.